In this lesson for CBSE and NIOS chemistry, we will build an intuitive picture of Heisenberg's uncertainty principle and connect it to electron clouds and orbitals in atoms. First, the definition. It is impossible to measure simultaneously and exactly both the position and the momentum of a particle. Mathematically, we say, delta x times delta p is greater than or equal to h bar over 2. Here, delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar equals h divided by 2 pi, approximately 1.055 times 10 to the minus 34 joule second. This inequality captures a fundamental limit of nature, not a limit of our instruments. Let us visualize the complementary nature of position and momentum. On the left, we show a probability distribution in position, and on the right, in momentum. A narrow position distribution means position is precise and delta x is small, and then necessarily the momentum distribution becomes wide. So delta p is large. If we widen the position distribution, the momentum distribution becomes tighter. Watch the curves change together. Now position gets very precise, momentum spreads out. Now position is broad, momentum becomes sharp. Why does this matter in chemistry? Because electrons cannot be pictured as tiny balls on precise circular paths. The uncertainty principle tells us that if we try to pin an electron's position down, its momentum becomes very uncertain, so a sharp orbit is not meaningful. Instead, we use probability clouds called orbitals. Let us compare a Bohr-style orbit and a fuzzy electron cloud. We cross out the fixed orbit picture, and we replace it with a cloud showing where the electron is likely to be found. Example calculation. Suppose we localize an electron within 1.0 times 10 to the minus 10 meters, about 1 angstrom, a typical atomic scale. Using the inequality, delta p is at least h bar divided by 2 times delta x. Substituting the numbers gives roughly 5.3 times 10 to the minus 25 kilogram meter per second. This large momentum uncertainty implies a significant uncertainty in kinetic energy, about 1 electron volt on this scale. In atoms, electrons are described by wave functions that solve Schrödinger's equation under boundary conditions. The allowed solutions are labeled by quantum numbers n, l, m sub l, and m sub s. These give us orbitals with characteristic shapes like s and p. The uncertainty principle supports this picture. Electrons occupy fuzzy regions, not precise paths. Key points to remember. State both the verbal and the mathematical form. Emphasize the complementary nature of position and momentum. Connect the principle to electron probability clouds and orbitals rather than precise paths. This is a fundamental property of quantum particles. And that is Heisenberg's uncertainty principle in action for chemistry. It justifies why we speak of electron clouds and orbitals instead of precise paths.